So this is the first of several lessons looking at implicit differentiation, which is the process of differentiating equations that are implicitly defined instead of explicitly defined. And essentially, an explicitly defined equation is something set up like y equals, and over here all you have is some expression involving the only variable being x. Something like that is what we call an explicitly defined equation, and that's what we've been differentiating so far. An implicitly defined equation is like what you see right here, which is the equation of a circle with a radius of 5. It's not solved for any particular variable, and we call this an implicitly defined equation. Now this is actually not a function, right? A circle fails the vertical line test, but that doesn't matter. We can still differentiate it. And, you know, it can be a bit challenging, hence we're going to spend a few lessons on this. But in essence, when we're differentiating something like this, we want to think of one of the variables, usually y, in fact always y, just to be consistent, but we think of the variable y as being a function of x. Okay, so that variable y here, we think of it as being a function in terms of x, which is actually, if that sounds strange, it's completely standard. If I just look at what I've highlighted beside that, you see that expression all the time, y equals f of x, which means we think of y being a function of x. That's it. Let me just get straight to it. So let's differentiate this. And now if you're tempted to look at this and solve for y first, you can do that. You'll actually get y equals plus or minus two different radical functions. And you could differentiate each of those separately, but I don't need to do that, so I'm not going to do that. What I want to do right away is differentiate everything with respect to x. So I'm going to differentiate both sides right away with respect to x, which really means I want to differentiate on the left side. I want to find the derivative, and I'll do this fairly slowly. I want to find the derivative of x squared with respect to x, plus the derivative of y squared with respect to x, keeping in mind that y is a function of x. And I want to find the derivative of 25 with respect to x. Well, maybe I'll start with the easiest part first. I think the easiest part is the derivative of 25 with respect to x. 25 is a constant. The derivative with respect to any constant is 0. OK. In fact, I'll give myself some more space over here. So the left-hand side is 0. OK, next. The right-hand side is 0. The left-hand side, the next part, the derivative of x squared with respect to x is 2x. OK. Here's where things are challenging. I want to find the derivative of y squared with respect to x. And for this, I need to use the chain rule. So before I go on, keep in mind, if we did not think of y as being a function of x, if y was just some other variable, then this would equal 0, for the same reason that the derivative of 25 was 0. If we're differentiating with respect to x, but we don't have an x here, well then effectively all that's a constant, and so the derivative of any constant is 0. But again, like I keep saying, x and y are not unrelated. Y is not a constant. Y and x are related. They're related by this equation, x squared plus y squared equals 25. And so that's why this does not equal 0. If we were finding the derivative with respect to y, if we're finding d of dy of y squared, if we're finding the derivative with respect to y, then this would equal 2y, for the exact same reason that this equaled this. But again, that's not the case. And so what we have to realize here is we want to find the derivative of y squared, but knowing that y itself is a function of x, which is why we have to use the chain rule, because what we have here is function y, which is a function of x, inside a quadratic function, the power of 2. So we differentiate the outside function first, and the derivative of the outside function, the derivative of the power of 2, is we use the power rule, so I have 2 times y to the power of 1, right, which I don't really need, times the derivative of the inside function, which in this case is just y. Well, d dx of y, that is what we're trying to figure out. If I look right there, and I look right here, that's the same thing. That's what we're trying to figure out. dy dx is the same as d dx of y. So that's what I'm trying to figure out. So I'm going to rewrite this a little bit neater. I'm going to write this as 2x plus 2y times dy over dx equals 0. But that's what we're trying to find. So with that said, all I need to do now is isolate dy dx. That's the derivative we want. And so to isolate it, I'm going to subtract 2x from both sides, and then divide both sides by 2y. there we go. There's my derivative. So notice my derivative of this circle, because keep in mind the equation I gave you is a circle of radius 5. X squared plus y squared is a circle centered at the origin with a radius of 5. And so the derivative at any given point is negative x over y, where x and y represent the x and y coordinates of some point on that circle. And notice my derivative has two variables in it, which makes kind of sense, because if you look at the original equation, it has two variables in it, x and y. It wasn't solved for either of them. And so if I want to find the slope of this circle at any given point, I need to find the coordinates of a point on the circle, and then it's just going to be the negative x over y. That's it, and that'll tell me the slope at that point. So notice before I go on, in this case, the actual algebraic work wasn't long. The weirdest part is really what I spent most of my time on. Understanding that this here, how it led to this here. And again, so important that we realize that if we were differentiating with respect to y, then we wouldn't use the chain rule. Or if y and x were not functions of one another, then that would be a constant. But again, I talked about all those, and so I don't expect us to be super confident with this after one example, but I think we're ready to move on to the next example. So let me look at this. X cubed plus y cubed equals 6xy. Okay, you could graph this in Desmos. It doesn't really matter for what I'm looking at here. It's not a function, though. It fails the vertical line test. But who cares? I want to find the derivative of y with respect to x. Same idea as before. So like before, I want to start by differentiating both sides with respect to x. And I'll do this relatively slowly. So d dx of x cubed plus d dx of y cubed. Keep in mind again that y is a function of x. And then d dx of 6xy. Okay, so in this case, the easiest part is what's first on the left. The derivative of x cubed with respect to x is just 3x squared. Okay, next, that y there is a function of x, very similar to what we did before. Again, if y and x were not related, this would be a 0. The derivative of y cubed with respect to x would be 0 because it's a different variable. Essentially, y is a constant. But again, like I keep saying, x and y are not unrelated to one another. They're related to each other with this equation. And so I use the chain rule again. Where my outside function is the cubic function. So the derivative of that is going to be 3y squared times the derivative of the inside function. And the derivative of the inside function is d dx of just y. And again, that's what we're trying to figure out. That right there is same as dy dx. Now that said, quite often when we're using implicit differentiation, we use, instead of writing this, and there's nothing wrong with what I have right now, but quite often, just to make it a little bit faster, instead of writing dy dx or d dx of y, we just put y prime, quite often. Right? That and dy dx are the same thing. So that notation of just y prime, which we've seen a little bit earlier on, we tend to use lots with implicit differentiation. On the right-hand side, got to be careful. We have to use the product rule here. Because we have x times y. And so we got to use the product rule. And so I can kind of factor out the 6 here. Doesn't really matter. I'll think of it like, I'll do this in a few steps. I'll think of it as 6 times the derivative of x times y. I'll do it like this. I'll highlight these in different colors to make the product rule more obvious. So let me focus on this part. So the product rule, I have 6 times the derivative of x, which is 1 times y left alone, plus the other way around. X times the derivative of y with respect to x. Which again, you may be tempted to say 1, but that's a derivative of y with respect to y. But the derivative of y with respect to x, knowing that y is a function of x, is just y prime. And so here I use the product rule. But keep in mind, those brackets with the 6 are key, because all of that is being multiplied by 6. So really what I have on the left-hand side is 6y plus 6xy prime. That was on the right-hand side. On the left-hand side, I have 3x squared plus 3y squared y prime. All right. So I'm trying to isolate y prime. I got 1 there, I got 1 there. So at this point, I want to get there's a variety of ways of doing this, but I want to isolate y prime. I want to get all my y primes on the same side first. It doesn't really matter which way I do this. I'll just, I don't know, I'll bring this term over here. So I'm going to subtract 6x y prime from both sides, and I'm going to bring, therefore, this term over here, because that doesn't have a y prime in it. So I'll do a little bit of swapping some terms around. All right, so next, each of these terms on the left has a y prime. So I'm going to factor that out. And now if I divide both sides by 3y squared minus 6x, I have y prime isolated. Which is great. That's it. It's also pretty easy for me to notice that every single term can be divided by 3. So I might as well do that. And so a slightly simpler form is this. All right. So definitely getting more involved, and it all keeps hinging on this idea that x and y are related to one another, and we're treating y as a function of x. You could do this the other way around. You could differentiate everything with respect to y and think of x as a function of y, but you'll probably just confuse yourself even more. So I'm not going to do that. I'm always going to be consistent. In the end, it's always going to be equivalent. And in this case, it's also really easy to miss that part with the product rule. I mean, there's lots of challenging parts here. And again, it all keeps hinging on the fact that x and y are not unrelated to one another. We think of them as being functions of one another. Right, I think I just have one more example here. Yeah. All right, same idea. And so let me differentiate both sides with respect to x. Now at this point, actually, I would highly recommend that you pause this in just a moment and do as much as you can. Like, really try all of it on your own. Yeah, you'll probably make some mistakes. That's going to be more beneficial than just watching me do this without having tried it on your own. So at this point, if you haven't done so already, definitely pause it. Try this on your own. Look back at some of the previous examples. And again, in the end, we want to find the derivative of y with respect to x, or y prime. All right, so assuming you've tried this now, I look right here. That is probably the easiest part, or right up there. That's just 2x. All right. Next, I have to use the product rule here. Just like we saw in the previous question. So minus, and some brackets here. The derivative of x with respect to x is 1 times y left alone, plus the other way around. X times the derivative of y with respect to x, but knowing that y is a function of x, so that's just going to be y prime. But those brackets are really, really important. Okay, next. The derivative of the derivative of y squared with respect to x. So again, I have to use the chain rule here. And so first, the outside function in this case is the power of 2. So use the power rule. So I have 2 times y times the derivative of the inside function is just y prime. There's that y prime again, there and there. And on the right-hand side, the derivative of 7 with respect to x is 0. Okay, so really, these brackets here, I don't want to, if I forgot about these brackets, I'd have the wrong sign. But again, if you look at the step above, I was subtracting the derivative of x times y, so I have to subtract all these terms. So let me just clean this up a little bit. All right, so at this point, like before, I want to get my y primes together. First, any terms that don't have y prime, I want to bring over to the other side. And maybe I'll just kind of write this. I'll change the order of this slightly. Okay, so I really just rearranged my terms here. Take out a factor of y prime from the left-hand side, and we're pretty much done. And so y prime, or dy dx, whatever, is y minus 2x over 2y minus x. And so in doing so, to get to that, notice we have to use the product rule and the chain rule in our implicit differentiation. All right, so with that said, easy to miss things, especially stuff like in this case, that product rule. You know, it's really easy to miss the product rule, or even if we notice we have to use the product rule, it's really easy to miss the fact that we need to have these brackets here and here. And you know, if we miss that, we have the wrong sign. It's all about being methodical and careful. Give yourself time as you work through the first set of the homework questions for this.